Lesson 13, Acid-Base Titration Curves. A titration curve is a graphical representation of the change in pH as an acid or base is added in a titration. So when you plot on the y-axis pH, 0 to 14, and on the x-axis you add the volume of base added in milliliters, if you plot all the data, you get this very striking, nice shaped curve. And what we'll see is there's a steep section here, steep section of this graph, that the equivalence point is actually defined as the midway point at the steepest portion. In other words, it's halfway up the steepest portion. So what we often have to do is we often have to plot this data, or at least you will in university, find the volume at the equivalence point, and then of course figure out the concentration of the acid from there. Well, how do you find this from an equivalence point? Well, there are two methods you can use. One method is to actually draw a pair of parallel lines, and then draw the perpendicular bisector of these lines. Make sure these are square. And if you measure this distance from here to here, right there to there, at the midway point, that will be the equivalence point. Now that's one technique. However, if I just erase all that stuff there is another method that you can use, and this is actually a pretty elegant method. If you if you drew this out on paper and you took a compass and you drew a circle that fit perfectly in the sort of, I guess you could call it, or I'm going to call it, the sort of armpit of this curve, and you draw another circle of the same diameter, forgive my artistic ability, where the center of these two circles, where the line between them crosses the graph, that's the equivalence point. That's important. It doesn't matter what size circles you use. You should use circles that fit nicely against the curve. But if you do them correctly, where they cross the graph will be the equivalence point. So then what you do is you do the dot down here and read the value off the graph, and that's 25 mils of base. Now, in a strong acid versus strong base titration, the equivalence point will be at about a pH of 7, which means you should use an indicator that has a pKa of around 7. Now, usually in a lab, when we do this in class, we'll do this indicator, this reaction, and we'll use phenolphthalein. Now, the problem with phenolphthalein is that phenolphthalein has a range of 8 to 10. So at 9, it's that perfect rose pink color that tells you when to stop. That's its end point. Now, 8 to 9-ish is up about, it's about there on the graph. Now, that you might think, oh, is that a problem? Well, actually it's not. Because this graph is so steep, the difference in volume of base added between a pH of 7 right there and a pH of 9 right there is, well, really it's really nothing. So phenolphthalein works absolutely fine. What you would not want to use would be an indicator that has an endpoint, in the range of, let's say, 1 to 3, somewhere in this range here. Because if you did, the indicator would tell you to stop at this point right here. You'd read that volume off the graph, and you'd get an error. It would be incorrect. The second titration we'll look at is when you take a weak acid and you neutralize it with a strong base in a titration. So here's an example. We have acetic acid and sodium hydroxide. Now, this graph, although it looks very similar, does have a couple of differences. One difference is the equivalence point is now actually higher. It's between 8 and 10. This would be a good time to use phenolphthalein because that would be perfect for this particular titration. Now, why is the equivalence point higher than 7 in this titration? Well, it's because one of the byproducts of this reaction, one of the things you produce, the salt, contains that ion, the acetate ion. And the acetate ion is a base. And as such, it causes the pH to be higher than 7 at the equivalence point. Another graph you can look at is strong acid versus weak base, and it's very similar to the last one in the sense that you have this region that sort of slopes gradually down, and then it gets steep, and then it levels off again. And you can find the equivalence point actually using the circle method there and draw a line between them, and away you go. This reaction, however, the equivalence point has a pH that's lower than 7, somewhere between 4 and 6. And that's because when you neutralize this weak base, this ammonia, you create conjugate weak acid. And that goes off and establishes equilibrium in the water and causes the pH to be lower than 7. Now, there's an interesting thing here. For titrations involving weak acids, the Ka of the weak acid can be found using this formula. Ka equals the concentration of H3O plus at 1/2 way to the equivalence point, or pKa equals pH at halfway to the equivalence point. Now, we'll not worry so much right now about polyprotic acids and titration curves, so for now, we'll just ignore this stuff right here. I want to focus on this equation right here and have a look at the previous graph for just a second. All right, so the one I want to look at is this actual graph right here, the second one here. And we're going to find the Ka of this acid from this graph. Now, we won't do this with the graph up here because, of course, we're titrating a strong acid. It doesn't really have a Ka because it's a strong acid and it's 100% dissociated. But with this weak acid down here, we can get this from the graph. First thing we need to do is figure out where the equivalence point is. Now, use whatever technique you want. If you want to draw, again, you would do this on paper or on the computer, but you draw 2 circles and you'd figure out where they meet and you draw the line, and that would give you the equivalence point. The volume here would be 25 mils. You would use that value right there coupled with the concentration of base you used to figure out the moles of base, and the moles of base would lead you to the moles of acid. You would divide by the volume of acid that you reacted, and then you would figure out the concentration of the unknown weak acid. That's fine, fair enough. But we're going to figure out the Ka of this acid using this relationship here. And how you do that is the pKa equals the pH at 1/2 of the volume to the equivalence point, which means that if the equivalence point's at 25 mils, you're going to go back on your graph until roughly 12.5 mils. You're going to draw a line up, you're going to hit the graph, and then you're going to draw a line straight over, and you're going to read this value right off of the pH scale right here. So this is 1, 2, 3, 4, not quite 5, let's call it 4.8. So pKa equals 4.8 because 4.8 is the pH at 1/2 the volume of the equivalence point. So if we want to find the Ka equals 10 to the negative 4.8, which is 1.6 times 10 to the negative 5.